The 8th video on second order responses looks at the dependence of convergence rates on the damping ratio. You'll remember then that this sequence of videos is looking at systems described by second order models a bit like this: d2x dt squared plus 2z to omega n dx dt plus omega n squared equals f. And we're looking at how the behaviour depends upon the coefficients, and in particular we're now looking at damping ratios zeta and natural frequencies omega n. This particular video is going to look at decay rates. How quickly does x of t settle at the steady state, and how does this depend upon zeta and omega n? Now what we're actually going to do is we're going to assume that the natural frequency is fixed, because that gives us better insight. So in other words, we're going to fix this term here, and all we're going to change is the zeta, and see how changing this damping ratio changes decay rates. An example first to start. Now what we should note is that these examples have been listed in a very particular order. So you've got overdamped at the top, and as you go down you see you've got a very underdamped system. So we've put them in that order just to so we can see the insights that come from what happens as I change the damping. Now first of all, with this overdamped system, what do you notice? I've got two real poles and they're quite widely spaced, minus 4.56, minus 0.53. As I reduce the damping slightly, it's still overdamped. I've now got a pole at minus 2 and another at minus 1, so still real poles but no longer widely spaced. Next I've gone to this situation here, and you'll see it's now underdamped because we've got complex poles. I've reduced the damping further still, so it's now becoming significantly underdamped. And what do you notice? Again, you've still got complex poles, the frequency of oscillation is getting faster, and the real part is changing. And finally, a very underdamped system at the bottom. So remember this order, because we're going to use this on the next two slides. First, let's look only at the underdamped examples. So what you remember is that as we went this way, zeta was going down. Now I don't know what happened there. Let's bring that back. So as we went down this table, zeta was getting smaller. Now what do you notice? You notice that you've gone from a real part of minus 1 to a real part of minus 0.5 to a real part of minus 0.1. So the real part, if I put that, so the real part is getting closer to the origin as zeta goes down. So as you reduce the damping, the real part of the root gets closer to the origin. Now on this graph you'll see we've plotted two exponentials just for information, e to the minus t, e to the minus 10 over t. And hopefully it's clear, this one's e to the minus t. Sorry, I've done that wrong. That's e to the minus t over 10. And the blue one is e to the minus t. So this one is faster. So as the real part gets closer to the origin, the response gets slower. So if you abuse the language, because fast is a relative term, you can see you've gone from fast convergence to slower convergence. So as the damping gets smaller, convergence seems to get smaller. What about this example then? Now we're looking at the two systems which were overdamped. So you remember, these ones were overdamped. And we had the one at the top which was very overdamped, widely spaced poles, and the next one which was slightly overdamped. Now what do you notice? The slowest pole for the very overdamped was minus 0.43. The slowest pole for the slightly overdamped was minus 1. So again, you see I've got an e to the minus 0.43 t here, and an e to the minus t here. And so the key thing is the widely spaced poles, or very overdamped, okay, if I write that, is the slowest. So it seems to be that as you increase the damping above 1 and you make the damping bigger and bigger, responses get slower. So preliminary observations. The fastest convergence occurred when the system is critically damped. That is, both roots are real and equal. If we increase or decrease damping from this point, we actually slow down convergence for that numerical example that we chose. So what we want to do next is see, is this a generic observation? Can we prove this for other systems? So let's look at observation 1. We know the closer the root of the characteristic equation is to 0, the slower the response. So let's consider a general form of the characteristic polynomial. There it is, p squared plus 2 zeta omega np plus omega n squared equals 0. And look just at the real part. So that's marked here, the real part. It's minus zeta omega n. What do you notice? We have said that omega n is fixed. We've fixed the natural frequency. And therefore, what you can see is the real part gets smaller or closer to the origin as the damping gets smaller. So clearly, as damping gets smaller, convergence gets slower. Now let's look at the other example, if we're overdamped. So if we're overdamped, we're looking at poles of this type of form here, p equals omega n times minus zeta plus or minus root zeta squared minus 1. Now, there's a plus and minus in here, so what we're actually interested in is which of these is closest to the origin. And what we can do, it's very easy to show that the one that's closest to the origin is the one that has minus zeta plus root zeta squared minus 1. So what we're going to do is sketch this as a function of zeta and see what we get. And what do you notice? If zeta equals 1, okay, then in essence what's in this bracket gives me 1. But as zeta increases, as the damping ratio increases, what I get out of this bracket, now I'm going to circle it, it's this bracket here which you're multiplying on omega n, what I get out of this bracket gets closer to 0. You can see at the top of this graph with zeta equals 5 we've got to a minus 0.1. So in other words, you get slower as zeta increases. So the response gets slower as zeta increases. So an example just to check. Look at these. Which do you think will converge to the steady state more quickly and why? So first let's calculate the damping. Now for all of these we know that omega n equals 4. We can see that because they've got 16. And therefore for this one zeta equals 5 over 8. For this one, zeta equals 8 over 8. For this one, zeta equals 20 over 8. And for this one, zeta equals 12 over 8. So clearly, this one here is critical damping, and so it's the fastest. And what you'll see is this one is underdamped, and therefore it's slower. This one is overdamped, so it's slower, and this one here is very overdamped, so it's very slow. So in conclusion, we focused on the normal form of second order differential equations in terms of damping ratio and natural frequency, and we've shown that convergence is fastest when the damping ratio is close to 1. Both increasing and decreasing damping about that point slows down convergence. When there's a challenge for you, you might want to think, is there an engineering explanation for why making the damping too small slows things down and making the damping too big slows things down? And you should be able to come up with some simple intuition as to why that makes good engineering sense.